So I'm going to be talking about drought impacts on forest water use in the southern Appalachians. And so prior to this, I don't think I realized exactly how management focused this conference was. So there is a lot of nitty-gritty stuff that you guys probably aren't super interested in. So I'll probably try to move through that pretty quickly and then get to the management stuff that is likely more interesting for all of y'all. So as we're probably all aware, climate change is accelerating the water cycle. And so even here in the southern Apps where we get so much rain, we're expecting to see more frequent and severe droughts under future climates. And so it's really important that we understand the feedbacks between forests and water so that we can incorporate that into management that's going to contribute to sustainable water-based ecosystem services. And that's actually a picture I got to take at Coweta, which was fun. Oh, can you guys hear me? I'm not sure how loud I'm speaking into the mic. Okay. Yeah, so this is actually at Coweta. I got to take that a few weeks ago, and I thought that was fun. And so one of the ways that the water cycle is accelerating is that evapotranspiration is increasing. And so some of the drivers of this change are rising temperatures and increasing evaporative demand, as well as longer growing seasons and shifts in species composition. And so when we're thinking about a forested watershed, right, the forest water use or transpiration component of ET is going to be the dominant part of the ET flux. And when we see that ET is increasing, that means there's a lot less water that's able to actually make it into the streams and support those water-based ecosystem services. And so when we think about, how do we sustain stream flow rates, or how do we manage for more drought-resilient stream flow, one thing that's come up is, can we manage the forest for lower water use species? And so that means over time, those forests use less water, there's less ET, and more water ends up in the stream. But there's sort of a lot of unknowns about how this might actually work at a broader landscape scale. And one thing that I'm sort of exploring in the next little bit of research I'm going to show is where on the landscape that management might be the most effective, or sort of give you the biggest bang for your buck in terms of water added to the river. And so one of the factors that we're assuming is pretty important in that is topography, right? So feedbacks between topography and vegetation sort of control how drought propagates across a mountainous landscape. And so incorporating that into the way we think about forest-water interactions is important. And so we've included elevation and hill slope, or that ridge-to-valley convergence, to think about the relationships between topography and vegetation. So for instance, temperature shifts along an elevation gradient will cause changes in forest composition, or lateral flow along a hill slope gradient is going to drive feedbacks between local water availability and vegetation, right? So soil moisture is going to organize along that hill slope gradient, and the wetter downslope positions will support higher water use and more mesic species in general. And what's kind of interesting is that we've actually seen that mesic to xeric gradient sort of become more dull over time, with the mesic species kind of creeping up slope. And so we think that probably does influence the way that water is cycling through the watershed. So the goal of this research is to understand what parts of the landscape forest water use is the most sensitive to drought, and then on the flip side of that, which parts of the landscape is forest water use continuing to use a lot of water during drought and maybe contributing more strongly to the stream flow deficits that we see. So we had two things that we were looking at: the relationship between ET and water availability, and then how that relationship changed over time. And we looked at those two metrics across these gradients in topography. And so that's the citation for that work, which you can see. And so our study region for this was the Blue Ridge ecoregion. You're looking at an elevation map there, basically, just so it wasn't boring to look at. And that's going to extend down from Georgia and up into Virginia. And next, to estimate the forest water use, we used remotely sensed evapotranspiration. And so different satellites produce different products. So we used two of them, the MODIS ET product, which is a 500-meter resolution, and then Landsat, which is a 30-meter resolution. And basically, we did a bunch of processing and ended up with these monthly anomalies of ET. And so that's going to be on a pixel basis so that you can compare spatially how water use is differing during drought. And then to look at water use, water availability, we used the standardized precipitation index, which is just a drought index. So you can see in that figure, the more negative the SPI value, the drier the conditions on the landscape will be. And we used this to categorize 3 levels of drought severity, so moderate, severe, and extreme. And then this is just the elevation, and for the hillslope gradient, we used the topographic wetness index. So a higher TWI value is going to correspond to a more downslope position on the landscape. So again, this is just zoomed in on Coweta because I figured that would be familiar. But the more yellow, higher values are going to correspond essentially to the streams because that's the most downslope position. We can probably skip past this. This is just basically saying that we took all that data and then we have a metric for the average ET response at drought peak and the way that drought responses have changed over time. And so now we can finally see, get an idea of how this is varying across the landscape. This is the average ET anomaly at drought peak. So a blue value means that forest water use increased at the drought peak, and a red value is going to correspond to a decrease in water use. And so a red is probably what we would expect, right, because there's a soil moisture deficit. So it's kind of interesting that we are seeing increased water use, and we'll kind of get into more of that in the next couple slides. So here we can see, what is this? This is the percent of the drought impacted forest that had above average water use at drought peak. And so what's interesting here is that at least 20% of the forests were using more water than average or increased their water use during drought. And so that's kind of important because when the forest uses more water, it exacerbates the streamflow deficits that we see downstream, right? And so this figure is a little overly complicated probably for this presentation. But so here we're looking at the ET response to drought at drought peak broken down by moderate, severe, and extreme drought across gradients in elevation and the hill slope. So again, a lower TWI value is more upslope. And so what we see is that the low elevation in those downslope forests are more drought sensitive, while the upslope and higher elevation positions are maintaining or even exceeding water use at drought peak. And so again, we can see that this is going to exacerbate. Well, what's probably happening is that when the upslope forests keep using up the water, a lot less water flows in that lateral flow component in the subsurface and reaches those downslope positions. And so that's part of what's contributing most likely to the more negative values we see downslope and at low elevations. So it's sort of those connected parts of the landscape are influencing each other by the way the water is able to flow. And next, we're going to look at the way that the relationship between ET and water availability has changed over time. It would have been nice to just look at how drought responses have changed over time, but because there's really not a ton of droughts that have happened since like the 80s, which is when this data set goes back to, we had to get like a little bit more creative. So on the left, we're looking at the correlation between SPI and ET. So basically, if you're thinking about a positive correlation there, when water availability increases, so does water use. And so from that, we can kind of infer that a stronger positive correlation means that that pixel is going to be more drought sensitive. And so this on the left-hand side is pretty much just confirming what we saw in the last couple slides, where those lower elevation and downslope positions have higher positive correlations, and we think they're going to be more drought sensitive. And then if we skip to the next and look over on the right-hand side, we're looking at the trends We're looking at the trend in the relationship between ET and SPI over time. So how has that sensitivity to water availability changed? And what we can see, and the figure is kind of weird to interpret, so if people are actually interested in this later, I can definitely go back to this, but I'll just give the overview. But what we can see is that ET is decoupling from water availability over time. And so basically what we're seeing is that forests are able to use more water during drought over time, which is like bad news again for the stream flow. And so big picture here is that ET has become less constrained by water availability at the expense of lateral flow. And so this is going to amplify the vulnerability of stream flow, downslope vegetation, and aquatic biodiversity. And so finally, getting to the management section, we can think about, could forest management be beneficial for water, in the Southern Apps? And so some of this should be familiar from the Coweta visit a couple days ago, but when we think about how mesification has impacted the landscape, and we're seeing this proliferation of those more mesophytic species, even in those upslope positions, I think a metric that we like to give is that a similarly sized oak and tulip poplar, the tulip poplar will use about 4 times as much water. And so when you see that over many, many acres, it is a big difference in how much water the forest is consuming and how much water can run off into the stream. And then when you couple that with climate change, you have something that you kind of really do need to address. And so something we've been thinking about is, can we manage the landscape for lower water use species? So again, more oaks, less maples and tulip poplars, and also a more open canopy, which I guess kind of naturally is going to come along with more oaks, right, for the regeneration piece. But this also means less biomass, which is just generally going to reduce forest water use. And so what's exciting about this is that it does correspond very nicely, I think, with a lot of the oak restoration work that's already happening and that TNC is interested in. And so we're interested to see, could water be a benefit of the oak restoration that's already happening on the landscape? And when we think back to the results we saw just like a couple minutes ago, we think about where on the landscape management might be most beneficial for water. It seems like it could be in those ridgetop positions or the higher elevations, so that we can make sure the lateral flow is actually making it down to the streams. And so this is something that I've been working on with TNC now. Julie DeMeester, who's I think she's the water coordinator for North Carolina, as well as Megan Sutton are sort of the TNC leads on this project. And we've been looking at the question, can forest management increase water supply and really base flow resilience to future drought and climate change? And so we're especially interested in base flow in this case, because it is the most important thing if we're thinking about sustaining aquatic biodiversity. That's what they really rely on. As well as during drought, we don't have storm flow during drought because there's not precipitation falling. So base flow is what we're the most worried about. And so to do this, we are using the forest landscape model, Landis 2, which Louise gave us all a great introduction to yesterday. And so we're coupling these management scenarios along with different projections of climate change and drought to understand how that might influence the forest, and in turn, how that would influence the water supply on the landscape. And so with this, we're really thinking about a few specific questions. The first being, how much management, like what scale of management is required at the landscape to make a noticeable impact on water supply. So if we think about a watershed, like what percentage of basal area maybe needs to be flipped from those mesophytic species to the xeric species. And then as well, how often do we need management? And that's something that a lot of y'all would probably be more familiar with, right? Because it's thinking about how much management do you need to flip a forest back to that xerophytic dominance. And then also, how long would the impacts of management last? And how do we really think about scaling that up to the landscape if we want this to be impactful to a regional water supply. And so I think that's the real benefit of having a model in this case, because there's a lot of unknowns. It would be a shame to just start, throwing some crazy ideas on the landscape willy-nilly and then have to wait 40 plus years to really see what the result is. So we can luckily have all of you with all of your knowledge about management, and then coupled with all of the field data from CAWIDA, which has been really, really important in actually calibrating that model to get a sense of the answers to some of these questions. And so it has been and will continue to be super important that we are engaged with managers and get y'all's feedback on the type of oak restoration management that's actually being put on the ground, because we do want to incorporate management that's realistic to the region, and hopefully so the results can be beneficial to you all and actually usable, right?